For as long as we've been trying to build intelligent machines, there's been this fundamental, really deep conflict about what intelligence even is. Is it a product of pure, clean logic, rules and symbols, or is it something a little messier, something that emerges from a complex, interconnected network? This split has defined the entire history of artificial intelligence.
To really get a grip on this divide, we have to rewind the clock, back to the very beginning, before AI even had its name. In 1948, a mathematician named Norbert Wiener coined the term cybernetics. He saw this profound parallel between how living things in these new machines seem to operate. The key idea was universal. How does any system, whether it's biological or mechanical, take in information, process it, and then act to achieve a goal? This one question would plant the seeds for two radically different answers.
So here's our game plan for this explainer. We're going to trace this intellectual battle. We'll start in the age of cybernetics, then we'll explore the two competing blueprints for a mind that came out of it, see why that first wave kind of stumbled, how the second one reemerged, and finally, we'll ask the big question, has this debate ever really been settled?
All right, so let's set the stage. The middle of the 20th century was really the dawn of a whole new way of thinking, and it was all driven by this new science of cybernetics.
Okay, so the absolute heart of cybernetics, it's all about feedback. Just think of a thermostat in your house. It senses the room's temperature, it compares that to the goal you set, and then it sends a corrective signal to the furnace to either turn on or turn off. This simple loop allows a machine to be self-regulating, to seem purposeful, without any magic involved, just information and control.
And what was so radical about cybernetics was its focus. It didn't really care what a system was made of, whether it was flash or wires. It cared about how it was organized. So for the first time, there was this universal language to describe a guided missile, the human brain, or even a social system, using the exact same principles of information, feedback, and control. This was the intellectual soil from which AI was going to grow.
So cybernetics kind of threw down this gauntlet, right? It asked, how do complex systems achieve their goals? And in the brand new field of AI, two very, very different answers started to emerge, and that created this fundamental schism.
And this really breaks down the two opposing camps. On one side, you've got symbolic AI. Some people call it good old-fashioned AI. They argued that thinking is basically just computation. The idea was to represent the world with abstract symbols and then manipulate them with logical rules, all inspired by pure mathematics. And then on the other side, you have connectionism. They said, no. To build a mind, you have to model the brain. They believed intelligence wasn't something you programmed. It was something that emerged from the complex dance of simple, interconnected units, just like neurons.
Yeah, this quote right here, this is basically the central gospel of symbolic AI. The crucial thing to understand is that Alan Newell and Herbert Simon weren't just proposing a method, they were making a bold scientific claim. They were arguing that any system capable of general intelligence, whether it's you, me, or some future computer, would, if you broke it down, turn out to be a physical symbol system. To them, thinking is symbol manipulation. Period. Now, the connectionists, they had a completely different take. They looked at the brain's wetware, the billions of neurons firing all at once, and they said, that's the blueprint. Forget all this high-level logic. Intelligence has to be built from the bottom up. Knowledge isn't a list of facts and rules that you program in. It's the pattern of connections between artificial neurons, a pattern that's learned through experience.
So, for the first few decades of AI research, the symbolic, logic-based approach was king. It was absolutely dominant. It had some amazing early successes, but it eventually slammed into a very, very hard wall.
And look, to be fair, the early results were pretty stunning. These symbolic systems were absolute masters of things that we humans find really difficult, like formal logic, chess, and complex mathematical puzzles. To the researchers at the time, it really seemed like they had cracked the code of intelligence and were on a clear path to solving the whole thing.
But here's the thing. They ran into this huge problem. Brittleness. A symbolic system might be a chess grandmaster, but it would have no idea that you can't push on a rope. And you might ask why? Well, because every single little piece of knowledge has to be explicitly programmed in as a rule. The real world, with its infinite exceptions and messy contexts, just couldn't be captured in a finite set of rules. So when these systems saw something they hadn't been explicitly programmed for, they didn't just get a little worse, they just broke.
So after a period we now call the AI winter, where, funding and interest just kind of dried up thanks in part to this brittleness problem, the dormant connectionist idea made a huge comeback.
So what fueled this comeback?
Well, a few things really came together. First, the hardware finally caught up. Massively parallel computers could actually mimic the brain's architecture in a way older machines just couldn't. Second, brilliant new learning algorithms were developed. But most importantly, these networks showed properties that the old symbolic systems just lacked. They were fault-tolerant. You could damage one part and the whole system wouldn't crash. And they had this thing called associative memory. They could see a piece of a pattern and recall the whole thing, which directly addressed that old brittleness problem.
And that brings us right up to the modern era. The connectionist approach has reemerged with just incredible force. But the real question is, has it actually settled this foundational debate for good?
I mean, think about it. When you hear about AI today, doesn't matter if it's image recognition, self-driving cars, or large language models, you are almost always hearing about the descendants of that connectionist dream. Deep learning is, at its core, just scaling up these artificial neural networks to sizes we never thought possible, and then training them on unbelievable amounts of data.
But there's an even deeper argument here that goes way beyond just how we build these things. Symbolic AI is really a theory of instruction. A human programmer explicitly tells the machine how to think. But a lot of biologists and neuroscientists argue that real intelligence works by selection. The brain doesn't get a program installed that has this huge variety of possible connections, and experience strengthens some while it weakens others. It literally learns what works by interacting with the world.
And that, right there, really gets to the philosophical heart of this whole thing. Is intelligence a precisely defined set of logical operations that we can design and build, like some intricate clock? Or is it more like gardening, something we can only create the right conditions for, cultivate, and then just watch as it grows into something complex and, maybe, a little unpredictable?
So where does all this leave us? I mean, the incredible success of deep learning really feels like a knockout victory for the connectionist, brain-inspired model. But if you look closely at modern AI, you'll start to see these hybrid approaches, structures that seem to blend this powerful learning with something that looks an awful lot like logic. So maybe the debate was never about which side was right, but about figuring out how to eventually bring them together. The one thing that's for sure is that the echoes of this conflict from over half a century ago are still shaping our future.